Okay, this will be the very first of the test corrections that will be done by Edpuzzle. This will be cover problems 1 through 10 for the Unit 3A Classical Probability Multiple Choice Test. All right, so, and you will need to write down everything that I have written down, otherwise you will not receive credit. So here we go. The number of hybrid cars a dealer sells weekly has the following probability distribution. So they're telling me that this just represents the number of cars. Probability of 0 cars is 0.11, probability of 1 car is 0.28, probability of 2 cars is 0.23, et cetera, et cetera. The dealer purchases cars for $21,000 and sells them for $24,500. There's a fixed cost for the showroom. The profit in dollars for a particular week can be described by this function. What is the standard deviation of y? So they're asking for the standard deviation of y, and they told us y happens to be the profit, but they're looking for standard deviation. Unfortunately, we don't have the standard deviation. We don't know how many cars we've sold. Since this is a multiple choice, I don't need to show all my work. I just need to plug in. So I'm going to go to Stat Edit. And you can see that in Stat Edit, I've entered the table values. By entering the table values, I can calculate the average number of cars sold, or I can calculate the standard deviation of the cars sold. So I'm going to just go press Stat, followed by Calc, one variable statistics. My X-list is now 1, my Y-list is now 2. Press Enter a couple times, and I find out that my standard deviation for the number of cars I sold is 1.42. The average number of cars is 2.15, but the standard deviation is 1.42. That is the standard deviation of the number of cars I sold, but they're looking for profits. Well, to do that, I need to substitute this into that equation. So I do that, I go y equals 3,500 times 1.42 minus the 1,000. Now, I need to consider my rules for transforming and combining random variables. It's like, yes, we can multiply spread, because standard deviation is a measure of spread. We can multiply that by a constant, but we cannot subtract the constant. That needs to go away. So I should be able to take my calculator and go 3,500 times 1.42. When I do that, I end up getting 4,970. And if you'd cover it at more decimal places, you're just going to have to choose the one that's closest. So our answer to number 1 is C. Okay, so you need to make sure you've written that down so that you will understand what you did. And once again, enter the information into Stat Edit. All right, our next problem. Problem number 2, events D and E are independent. That's a key word. They're telling us they're independent, and the very fact that they're independent tells me that the probability, or if independent, the probability of D and E equals the probability of D times the probability of E. Well, when I read it, they say D is 0.6, and they don't give me E, but they tell me the probability of D and E, which is that's my intersection symbol, is 0.12. Well, I can divide that out and go 0.12 divided by 0.6 equals 0.2. So when I divide this by 0.6, I find out that E equals 0.20. Then I look at my answer choices, because it says which of the following is true, and all of these have an or. Well, remember, or means union. So this is going to be the probability of D union E equals the probability of D plus the probability of E minus the probability of D and E. So they're looking for the or, they're looking for this union. Well, we know that D they gave us was 0.6. We know that E is 0.20. And we've already calculated our intersection as being 0.2. They gave us our intersection, and they told us our intersection was 0.12. So I should be able to go at this point, 0.6 plus 0.2 minus 0.12. And when I do that, I end up getting 0.68. So the probability of D or E is 0.68. All right, so each person in a random sample of adults indicated his or her favorite color. The results are shown in the table below, are reported by age group of the respondents. If the choice of color is independent, so they're saying if. In other words, they're asking us to pretend they're independent. If a choice of color is independent of age group, which of the following is equal to the expected number of respondents who are aged 30 to 50. So I want the 30 to 50 group, which is right here, and preferred green. Okay, so reality is what actually happened is this is the actual. The actual is we have 35 out of 314. But they said if, so in other words, they want to pretend that they're independent. So if we pretend they're independent, I should be able to take, at this point, the probability of A times the probability of B and have that equal the probability of A and B, because that's true if independent. So that would be 99 times 99 over 314 times B, which would be 108 over 314. Now this ends up giving me a probability, all right? Well, what's expected value? Expected value equals N times P. My sample size times my probability. So in other words, I need to multiply this by my sample size, which happens to be 314. Those cancel out, and I end up getting 99 times 108 over 314. So my answer choice is A. Now I recognize some people struggle with, why do you multiply? Consider this. If you made 80% of your basketball shots, you made 80% and you took 20 shots, you'd go 0.8 times 20 equals 16 to find how many you would expect to make. So once again, this just gave me my probability. So then I needed to come back and multiply by my sample size. Right. So that takes care of that problem. We're moving on to problem number 4. A complex electronic device contains 3 components, A, B, and C. The probabilities of failure for each component in any one year are 0.01, 0.03, and 0.04. If any one component fails. All right. If any one component fails, the device will fail. They tell us they fail independently. This tells me I can do something with multiplication. What's the probability that this device will not fail in 1 year? All right, for the device not to fail, this can't fail, and this can't fail, and this can't fail. So the probability that the first one doesn't fail is 1 minus 0.01. The probability the second part doesn't fail is 1 minus 0.03. And the probability the third one doesn't fail is 1 minus 0.04. Now, they told me they were independent, so I can multiply them. So this is going to be basically be 0.99 times 0.97 times 0.96. That's the probability of not failing, and not failing. And that's what they wanted. They wanted the probability that the device will not fail. So in this case, 0.99 times 0.97 times 0.96. We end up getting 0.9218. My closest answer is D. This is the probability the device will not fail. On the other hand, if I had done 1 minus those values, I would have found the probability that it did fail. Okay, so the probability it does fail is about 0.078. Okay, a mathematics competition uses the following scoring procedure to discourage students from guessing on the multiple choice test. By the way, I think this goes back to when I was growing up and the PSAT and the SAT counted points off if you had the wrong answer. So, right, for each correct response, the score is 7. For each question left unanswered, the score is 2. For each incorrect response, the score is 0. All right, so correct is 7, blank is 2, incorrect is 0. If there are 5 choices for each question, what's the minimum number of choices that the student must eliminate before it's advantageous to guess among the rest? Let's just say my answer choices are A, B, C, D, and E, and we don't know which one is correct. Well, the probability that I guess the correct response out of 5 would be 1/5. If I do guess it correctly, I get 7 points. 1/5 times 7, so basically 7 divided by 5, would tell me that, you know what, I expect to guess and get 1.4 points. But if I just left it blank, I would have been given 2. So if I can't eliminate 0, if I eliminate 0, in other words, I have to guess out of 5, this is not a good thing because it's less than if I just left it blank. On the other hand, if I had eliminated 1, now I have 1 out of 4 choices. Well, 1 out of 4 times 7 is basically 1.75, and that's still less than the 2 points that I would get if I left it blank. So I would have been better off if I can only eliminate 1. I'm only expecting to get 1.75 points. I'd be better off leaving it blank and getting the 2 points for leaving it blank. If I can eliminate 2 answers, so I've now eliminated 2 answers. My probability of guessing correctly is 1/3 because I only have 3 answer choices. I get 7 points for that if I guess it correctly. And that ends up being 2.33333. All right, if I can guess that 2.333 is greater than 2. So guessing at this point gives me 2, I would expect to get 2.3 correct points, as opposed to the 2 points for leaving it blank. So I would be better off if I can eliminate 2 than leaving it blank. If I can eliminate 2 answer choices and guess, I should go ahead and guess. I'm better off doing that. All right, moving on to number 6. And by the way, that's a challenging problem as far as I'm concerned. Problem number 6, the probability the new microwave oven will stop working in less than 2 years is 0.05. The probability the new microwave oven is damaged during the year and stops working is in less than 2 years is 0.04. The probability the new microwave oven is damaged during delivery is 0.1. Given the new microwave is damaged during delivery, what is the probability it stops working? All right. So we have basically a couple different variables at work. And when we have a couple different variables, I like to look at this as potentially as a table problem. So when I look at these values, I said the probability a new microwave oven will stop working in less than 2 years is 0.05, and that happens to be associated with one variable. So at that point, I can sit there and go, you know what? I've identified a number that is associated with only one variable. So this is associated with stops working. All right. The probability it stops working is 0.05. That means the probability that it does not stop working, in other words, it works, is 0.95. We know this is one whole. Continuing on. The probability a new microwave is damaged during delivery and stops working in less than 0.2 years is 0.04. Well, this is damaged. So this is damaged and stops working. So this is a 2 variable. I'll come back to that one in just a moment. And then it says the probability a new microwave oven is damaged during delivery is 0.1. This is just damage during delivery. It doesn't say anything about a second variable. So this is also one variable. So this would be damaged and not damaged. Well, this is only associated with one variable, so I can go ahead and record it right here, 0.10. This becomes 0.90. All right. So we need to go back to the third variable they gave us. And it says the probability a new microwave is damaged during delivery and stops working in less than 2 years is 0.04. It doesn't say if, it doesn't say given, it doesn't say from the group, it just says the probability that both things happen. So this one's not conditioned, and because it's not conditioned, I can record it just the way it is. All right, and I could actually finish out the table at this point. This would be 0.01, this would be 0.06, all right, and this right here is going to be 0.89. So I finished out the table, although it wasn't necessary to do so. It says, what is given that a new microwave is damaged? Well, as soon as they say given, I know I'm working with intersection over given. And in this case, damaged is in the denominator. So given that a new microwave is damaged, so that's 0.1. And remember, I say, all right, we should go ahead and circle this. So it's given it's damaged. What is the probability it stops working? Well, if I intersect it, it's like, oh, my intersection is at 0.04 because that's what got circled twice. So 0.04 divided by 0.1. All right. So 0.04 divided by 0.1, we end up getting 0.40 or 40%. So there's a 40% chance that if it were given that it was damaged, that it's going to stop working. All right. Number 7. The probability of winning a certain game is 0.5. So in other words, we expect to win it the game at 50% of the time. If at least 70% of the games in a series of games are won, the player wins a prize. So I'm supposed to win 50% of the time. All right. So if I flip the coin, I correctly call heads 50% of the time. But to win, I have to call it 70% of the times. So in this case, the law of large numbers is not in my favor. I need to play it as few times as possible in order to win. All right. So I need to play it as few times as possible. The law of large numbers says that the more we repeat something, the closer it becomes to the theoretical. So the closer it comes to 50% this time, and we do not want to be close to the theoretical. So we should choose the smallest sample. If we wanted to be close to the theoretical, we should choose the largest sample. But since we want to be close, since we don't want to be close to the theoretical, we should choose the smallest. So the smallest in this case happens to be 10. So our answer is we would like to just do it 10 times because I have a better off chance of flipping 7 heads than I would 14 heads. And if you don't believe me, let's try this out. The probability of flipping heads is, if we had to do it 10 times, if we do this thing 10 times, I need to get 70%. 70% of 10 would be 7. So 0.5, that's my probability to the 7th power. Would I rather have that, or would I rather have 0.5 to the 14th? That 14 came from, this is 0.10 times, or excuse me, 0.7, the 70% I have to win, times my probability, times 10. This is a 70% I have to win times 20, which gives me 14. And then if I did 0.5 here, it'd be 0.7 times 100. So I'd have to win it 70 times. If I take my calculator and check those out, I can go 0.5 to the 7th. Not very likely, but it's more likely than 0.5 to the 14th. And it's certainly more likely than 0.5 to the 70th. As you can see, those numbers are getting substantially smaller the more times I play it, because I'm getting farther and farther away from the theoretical. Okay, all right. Problem number 8. The number of points obtained in one game is independent of the number of points obtained in the second game. When the game is played twice, as soon as they say the game is played twice, I'm probably going to have to set up a sample space. They tell me up here the number of points scored in a game has the distribution. So if I play the game once, there's a 40% chance I get 0. If I play it, play it once, there's a 30% chance I get 1 point, and there's a 30% chance I get 2 points. Obviously, those sum up to be one whole. So the sum of the number of points could be 0, 1, 2, 3, or 4. And the way they did that is they said, they go, well, you could get 0 on the first game, and then 0 on the second. You could get 0 and 1, 0 and 2. You could get 1 and 0, 1 and 1, 1 and 2, 2 and 0, 2 and 1, and 2 and 2. If I add these up, that becomes 0. This becomes 1. These become 2. These become 3. And that becomes 4. All right, so that gives me how they came up with their distribution. So we want to know if y represents the sampling distribution played, for which value y will the probability be the greatest? Well, to get 0 points, I have to have a 0 and a 0, which means 0.4 times 0.4, and the probability of that happening is 0.16. To get 1 point, I have to have a 0, 1, or I could have a 1, 0. So the probability of a 0 would be 0.4. The probability of a 1 is 0.3. Or I could have it the other way and get a 1, which is 0.3 times 0.4. But it's either this or that. It's either this one or that one. So I have to add them. So this ends up being 0.12 plus 0.12, which is 0.24. Then we go to the 0, we go to 2, and 2 is 0, 2, 1, 1, and 2, 0. 0, 1 is going to be 0.4. 0, 2 is 0.4 times 0.3. Wrote that poorly. 0.4 times 0.3 plus 1, 1 is 0.3 times 0.3. And then 2, 0 is going to be 0.3 times 0.4. All right. And when I multiply all that out, this is going to be 0.24 plus 0.09 equals 0.33. Then I have to come up and I have to do, all right, for 1 and 2 and 2 and 1. So 1 and 2, 2 and 1, this is for the 3s. Oops, because those sum to 3. 1 and 2 would be 0.33 times 0.33 plus 0.33 times 0.33, and that is 0.09. And then finally, we get to do the 2 2s. And the probability of a 2 is 0.3. So 0.3 times 0.3. Oh, this is 0.18, excuse me. I didn't add that. This is 0.09. So those are my probabilities, okay? And more neatly written, so that might be easier for you to copy down. This right here, 0.16, 0.24, 0.33, 0.18, and this is 0.09. Well, which one occurred most often? Well, 2 occurred most often. So my answer for this question happens to be 2. All right. Once again, it really, really helps to set up the sample space whenever you're playing 2 games of something. All right. All right. The next one. another sample space, but this time it's with dice. Each of the faces of a fair six-sided number cube or dice is numbered with numbers 1 through 6 with different numbers appearing on each face. 2 number cubes will be tossed and the sum of the numbers appearing on the face lined up. What's the probability the sum will be 4, given that it is less than or equal to 6? Well, remember, they said given. So that means I'm working with an intersection over given, and what I was given was 6. So 6 has to be in the denominator, and it says less than or equal to 6. So I went ahead and took time and made a sample space. And these values right here are less than or equal to 6. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 values that are less than or 6. And it says, what's the probability that the sum will be 4? Well, my 4 values are 1 and 3, 2 and 2, and 3 and 1. So in this case, 3 out of 15. So 3 out of 15 will be my best choice for that answer. And that answer choice happened to be C. All right, this next problem will be the last problem for this particular video. All right, so a police officer is using a radar device to check motorist speeds prior to beginning the speed check. The officer estimates that 40% of the motorists will be driving more than 5 miles over the speed limit. Assuming the officer's estimate is correct, what's the probability that among 4 randomly selected motorists, they will find at least 1? Well, as soon as we say at least 1, we know we're doing a complement, because we could have 0 motorists speeding, 1 motorist, 2 motorists, 3 motorists, and 4, because we're basically looking at possible at 4 randomly selected motorists, and we want at least 1. So we're interested in these values. So it's at least, so we're probably going to look at doing 1 minus the probability of 0. Well, remember, whenever we're working with an at least scenario, we do the opposite of what they're interested. They said they wanted at least, they said they wanted the numbers exceeding the speed limit. So we're going to have to do the opposite of that. They say 40% speed, so the opposite of that is 0.6. So what we're looking for, the opposite of what they asked for, is 1 minus 0.6 to the 4th power. On the calculator, 1 minus 0.6. I like to use the caret button right here, or the arrow button, to the 0.4. And I end up getting 0.1848. All right. So let me see what I did wrong there, because I did not get that answer. I'm going to pause this for a second and figure out what. Okay, let's try that again. 1 minus 0.6 to the 4th power. Apparently I hit a button incorrectly. So anyway, 0.8704. Our answer choice should be D as in dog. Okay, and again, at least 1. So as soon as I say at least, I know it's a 1 minus, and I want the 1 minus the, and I always do the opposite of what they asked for. They asked for speeders. So in speeders was the probability of speeding was 0.4. So 1 minus 0.4 gave me the 0.6, which was the opposite of what they asked for. So 60% are not speeding. So 1 minus having no speeders. Because basically, if I covered up the 1 minus part, I said, you know what? 0.6 to the 4th power. That means there's about a 13% chance that among 4 cars, none are speeding. There's about a 13% chance that none are speeding. So 1 minus that tells me there's about almost an 87% chance that there's at least 1 speeder. All right.